In this video, we will discuss the fixed point iteration method for solving systems of nonlinear equations. The fixed point iteration method for finding roots of a single equation that we discussed in Chapter 4 can be extended to nonlinear systems of equations. And this is in fact a simple extension to the iterative methods used for solving systems of linear equations that we discussed in Chapter 5. So the fixed point iteration method proceeds by rearranging the nonlinear system such that the equations have the form x is equal to f of x. So x1 is equal to f1 of x1, x2 up to xn, x2 is equal to f2 of f1, x2 up to xn, down to xn is equal to fn of x1, x2 up to xn, where for every I up to n, fi is a nonlinear function of the components x1, x2 up to xn. By assuming an initial guess, the new estimates can be obtained in a manner similar to the Jacobi and Gauss-Seidel methods described previously for linear systems of equations. If the components of the vector x after iteration I-1 are those shown here, and after iteration I, the components are those shown here, then our usual stopping criteria would be that the approximate relative error, which is the norm of xi minus xi minus 1 divided by the norm of xi, is less than or equal to some error threshold epsilon s. So this says the norm of our present iteration minus our previous iteration divided by the norm of our present iteration, where norm of xi minus xi minus 1 is shown here using the Euclidean norm, and the norm of xi is shown here again using the Euclidean norm. And as we discussed before, other norm functions would be applicable as well. So let's go through an example to illustrate the procedure. We want to use the fixed point iteration method with epsilon s is equal to 0.0001 to find the solution of the nonlinear system of equations given here. So our first equation is x1 squared plus x1 times x2 is equal to 10, and our second equation is x2 plus 3x1 x2 squared is equal to 57. So we first want to rearrange the equations to the following form. We need our functions to be in the form x is equal to f of x. So this is a possible arrangement of our two equations. So our first equation becomes the first line here. So x1 is equal to 10 minus x1 squared over x2. And our second equation becomes the second row here. x2 is equal to 57 minus 3x1 x2 squared. So using an initial guess of x1 is 1.5 and x2 is 3.5 yields the following. So from our first equation, we plug in our estimate of x1 and our estimate of x2 to calculate our new estimate of x1. So x1 is equal to 10 minus 1.5 squared divided by 3.5. So this means x1 at our next iteration is 2.21429. We do the same for x2. So we plug in our the values that we know. So the equation was 57 minus 3x1 times x2 squared. So we've already calculated our x1, so we can use our current value in estimating x2. And then we have not updated our x2 yet, so we'll use our previous one, which was 3.5. So this gives us our next estimate for x2 as negative 24.37516. For the next iteration, we do the same thing. So again, x1 is given by our first equation, so 10 minus x1 squared. So now we're using our updated value for x1, which we put in here, divided by x2, which is again our updated value. So our next estimate for x1 is negative 0.20910. And we do the same for x2. So our equation again was 57 minus 3x1 x2 squared. So we put in our new value of x1 and our most recent value of x2, which was minus 24.37516. So this gives our updated estimate of x2 as 429 0.709. As you can see, it appears that the method is diverging, and if we continue the procedure, the method will very quickly diverge. So I've put together an example MATLAB script that calculates the fixed point iteration for this system, and these are the output of the first few iterations, and the method fails to converge. Alternatively, we can use another form of the equations as shown here. So our first equation can become x1 is equal to the square root of 10 minus x1 x2, and the second equation becomes x2 is equal to the square root of 57 minus x2 divided by 3x1. So using the same initial guesses, our first iteration goes as shown here. So x1 is equal to the square root of 10 minus x1 x2. So we plug in our values for our initial guesses for x1 and x2. And our updated estimate for x1 is 2.1794. Then we do the same for x2. And again, we're using our most recent value for x1 and our previous value for x2, because that is our most recent value for x2. So our new value for x2 is now 2.86051. And the approximate relative error can be calculated after the first iteration as shown here. So in the numerator, we've got the norm of our current estimate minus our previous estimate divided by the norm of our current estimate. So epsilon r is 2.595. And you can see using the same MATLAB script or the same MATLAB function that the method converges in 9 iterations using this formulation for our equations. And it converges to the solution x1 is equal to 2 and x2 is equal to 3. So you can see in a very similar way to the fixed point iteration method that we talked about in chapter 4 for finding roots of single equations, that the form of the equations x is equal to f of x does affect the convergence of the fixed point iteration procedure for a system of nonlinear equations as well.